wonderful afternoon session that we have put together. We had a bunch of great talks in the morning, lots of great discussion over lunch, following upon the topics presented in the morning. The afternoon session, a great lineup, and let's just start this off with Marc here, talking about relating bulge growth and quenching. Yeah.
Okay, hello. Thank you very much. I'm very happy to be here once another year. I'm starting to be a fan of Santa Cruz, and very happy to be here. So I'll talk about recent work on trying to relate bulge growth and quenching. I included this with artificial intelligence, but I've been talking about deep learning and artificial intelligence for 1 month now since I'm here. So I won't talk much about the technique. I will more focus on the science that we can do with it. And in this talk, this will be like a tool, but I will focus on the science. So the basic question we're trying to understand is why there's this relation between quenched galaxies and structure that you can see in many flavors. Quenched galaxies here in red points are smaller at fixed stellar mass. They are denser, which you see in the central density, and you see it in the scarcity index. And basically, these are relations that we all know. And the questions that we try to answer basically is where this relation comes from. We knew that there has to be some relation between the moment galaxy quenches and how it builds their bulge. And basically, there are several questions that I try to answer is, where do bulges grow? Do they grow while galaxies are still forming stars here in the main sequence? Do they grow in the process of quenching? Do they mostly grow when they are already quenched? Which is the same of answering the question, or how quenching affects galaxy structure. And this also needs to, you need also to answer the question, what are the mechanisms that build that bulge? We have many kind of mechanisms that have been invoked by theory, which include mergers, migration of clamps, VDIs, compaction, or also progenitor bias, which could be bias in your view of this connection. So I will try to address some of these questions with kind of new results, and these are basically a work in which most of it's from candles, in which we took 17,000 bright galaxies, lower than 23, and using a combination of GALFIT in multi-wavelength band plus some kind of artificial intelligence that I won't detail here, we have obtained like what we think are reliable bulge decompositions in several filters in the candle fields for all these galaxies here. So we have structural parameters of bulges and disks in different wavelengths, from the infrared to the bluer bands. And this allows you, by fitting stellar population models, to get kind of SEDs of bulges and disks. And this is kind of an attempt to break these degeneracies that most of the studies that I've been doing are based on global properties of galaxies. So here you get the SED of the bulge, the SED of the disk, basically, and you can get from these sizes, of course, stellar, which are the main parameters that we focus on here. You can get stellar masses of both components, and this means that you can estimate a kind of bulge to total ratio, but not light-weighted, but kind of taking into account the different mass to light ratio in the different wavelengths, and also rest frame colors, UVJ, which I will show you for the both components. So J, of course, since we are fitting only the optical bands, is kind of built on the extrapolation of the model. That's why I put a bemol here. So most of the results I will show you are kind of new and published based on this procedure. So I will show you some of the relations I've started to plot and the thoughts that I think arise from that, and I will be happy to have your feedback. Some of them are very preliminary. So the first, so these are some examples, for example, of these SEDs of a pure spheroid, a pure disk. You see how different they are. Galaxies which are clearly have two components. This is what we call a pseudo bulge, but I won't enter into details of that. Now, the first thing that you can start doing is looking now at the M-star sat formation plane at different redshift here, color-coded by the B/T now estimating stellar mass, so bulge to total ratio. disky galaxies here, bulgy galaxies over here, and you already see very clearly what we already know, basically, nothing very spectacular, but all this main sequence over here is dominated by blue points, so mostly low B over T's, while here in the quench population, you start seeing colored points with higher B over T's. Now, this is another view of the same plot with the Sersic index, but now color-coded with B over T in stellar mass. Now, what I find interesting here is that now you remove all these guys with the lower B over T 0.2, and this is what you get, basically. So this is now the view in which I've removed all the blue points, basically these guys over here. And you see now that there are these galaxies with bulge that are a bit everywhere. They are here and over here. While you don't have blue points here. This population is basically the same removing this object. So for me, and this is what I interpret here, this is a kind of evidence that bulge growth needs to start in the main sequence. Otherwise, you couldn't have this population. You would have expected at least blue points, some blue points over here. So at least the start of the growth needs to happen in the main sequence. This is another view of this. Now I'm showing you the bulge to total start. So in stellar mass distribution at different redshifts for quiescent and star-forming galaxies. And again, you see the same thing here. So you see an excess here of very low B over T's in the star-forming population, defined in UVJ, and here basically the fraction is 0. So again, this is another indicator, so the same view of this, that bulges grow in the main sequence, and probably this is telling you that there's no, at least an evident quenching channel without bulge growth. This is, of course, for the field. We know that there are red spirals somewhere, but probably you can find in denser environments. I don't know. The other thing that you notice here is that an excess over here, which you don't find super completely bulge-dominated galaxies in the star-forming population, which is kind of telling you that you need additional, somehow, an additional growth during or after quenching. But what I find also interesting here is that you have, in the intermediate B over T's, and this is what I was showing you before, the blue and red population are not so different. So they have a bunch of objects over here. We have bulge to total, intermediate, same morphology, but different star formation activity. And I believe that you can learn a lot on how the quenching process is going on by studying this population here. And I will show you some examples of that. One thing that you can start doing is, for example, plotting the structural properties of bulges and disks. And now this is the mass size relation that you all know. But now I'm plotting here, instead of the total mass, the mass of the disk for the blue points. And here I'm putting all disks together, independently if they are star forming or quiescent, all these together. Red, all bulges plotted as a function of the mass of the bulge for two redshift beams, but it's more or less the same for all redshifts. And here, the effective radius of the disk and the bulge. And basically, what you see, they are very different. So the green points, I won't enter into details, are what we call pseudo-bulges. But anyway, what you see is you have these two relations, and these are all bulges and all disks. So you include bulges that live embedded in disks and disks with a bulge component. The first thing when I saw that plot is that I realized that it's extremely similar to the one we all know from Van der Waals, in which you separate galaxies based on star formation. And basically, they look the same. While here, I didn't any cut in star formation. This is just total mass versus total RE, blue point star forming, red quiescent. In fact, the black lines here are reporting the fits over here. So you see, it's very, very similar. Now, what's interesting here is that in this plot over here, there are star-forming galaxies. And I'm focusing now on the bulge. I won't discuss the disks today. But now in this population over here, I plotted in blue bulges that live in star-forming galaxies, sorry for the A, and bulges that live in quiescent galaxies. UO is dominated by red points, but the blue points are galaxies, bulges at the same mass that live in star-forming galaxies. And basically, they look very similar. So now the relation is very, very similar. So again, this is pushing that even in these galaxies which are star-forming, the bulge is already built, and the structural properties of the bulge are the same than in the quiescent population. Which, for me, this kind of, and again, these are thoughts, means that quenching does not dramatically change the central structure, but when it's built here, and then when it quenches, the central structure, the properties of central structure of the bulge are the same, which, well, bulges in star-forming galaxies look like bulges, basically. Which is something that we would expect, nothing very surprising, but it's nice to see it in this resolved way. The other thing is that here in this population, again, it's not, again, I'm splitting again this population instead of on star formation activity on the B over T. So here you have bulges that live in different ranges of B over T. Again, you see it's dominated by bright points. That's why the bulge component behaves very similar than the total component for quiescent galaxies. But you have a population here of objects that are a bit over there or everywhere, mostly at lower masses, of course, but of intermediate B over Ts. And again, these bulges look like very similar. So, in fact, you have like 30% of massive bulges, more or less, above 10 to the 10, in this, that live in these disk-dominated galaxies. And in terms of structural properties, they look more or less the same. There's a bit of lower sizes over here that I will comment. But basically, for me, this is telling somehow that has to be a kind of similar formation mechanism. So if you think that these galaxies are completely embedded in huge disks, so these bulges, while these bulges are practically completely dominated by the bulge component, but the structural properties are very similar. I don't know if it's telling something about how these bulges form. I would comment more on this. So basically, if you go more into the details, and these are bulges, for example, in star-forming and quiescent galaxies, now I'm dividing by the median. You see that there's a small trend, basically. So 1 means they are exactly than the median relation. So you see that bulges that live in quiescent galaxies are a bit smaller, but it's than bulges that live in star-forming galaxies, but it's a 10% effect. This, for me, tells something about where bulges form, which I believe is in the main sequence. Now, this is again the same thing, that bulges living in different morphologies, so bulges completely embedded in disks, bulges that live in bulge-dominated systems, and you see that the median size is not very different. You have a trend to have smaller bulges in a disk-dominated system, but it's a 10% effect. This, for me, tells you something about the bulge formation mechanisms. And I will just illustrate this, for example, with a prediction from a semi-analytical model that just Francesco Shankar did a quick plot for me, in which basically this is the prediction a SAM makes on what should be at fixed mass of the bulge, the size of a bulge that lives in a disk, compared to the size of the bulge that lives in a bulge-dominated system. And you see there's a factor of 5 at fixed stellar mass, which the observation state is less than 10%. And this is because in SAMs, bulges that live here are basically formed by disk instabilities, which create smaller bulges, while these bulges here are basically formed by mergers completely and create larger bulges. And this is something that we don't see in the observation. So I don't know, this is something to explore. Now, and this is another structural property, and this is for my Santa Cruz colleagues, in which I'm plotting here the total stellar mass as a function of sigma 1, the central stellar mass density. And this is the plot that already Guillermo Barro did, in which you see that star-forming galaxies or non-compact galaxies tend to lie in a different relation than the compact galaxies over here, and this is the feed by Guillermo. So one thing, and what they can do is now plot this plot instead of as a function of the total stellar mass, as a function of the bulge. And you see that this relation that was kind of spread over here for blue and in a different normalization, when you put as a function of mass of the bulge, they tend to lie in the extrapolation of this relation. So you have a kind of more linear relation, kind of a one single power law between the mass of the bulge and sigma 1, which is something that you would expect, basically. Sigma 1 is related to the mass of the bulge. Now I'm going to speculate a bit more because I've been discussing with Sandy. Sandy says that probably this claims that sigma 1 is an indication of black hole mass. And maybe, so this is true, this is kind of an estimate of this relation. There is no well-known relation between the bulge, mass bulge, and black hole. And this is basically telling that as galaxies grow their bulge in this sequence over here, and they become compact, and they at the same time grow their black hole. Okay, I'm going now a bit step forward, and now trying to, so I've been looking at the structural properties, but also you can try to tell how this quenching process happens within the galaxy that you resolve. And basically, I'm focusing now on this population I just told you that have similar morphologies, but ones are star-forming, others are quenched. And by looking at those, you can try to understand how is quenching happening. Does it happen, starts in the main sequence, or does it happen at the same time, or does it happen already very brutally when it quenches? And basically what I did is taking these galaxies over here and divided between star forming and the UVJ. So these are the galaxies where they lie, and quiescent galaxies, which typically lie in the UVJ by selection, but the same morphology. Okay? And these are the stars over here, are the median values. So what you can do is now plot, and this is where I start to be more speculative and more noisy. This is very preliminary, but you can split now this population between bulges and disks. And for each black dot over here, plot its bulge and its disk in the UVJ. And this is what you get. A lot of noise. I've tried to estimate here the error bars. So these are the individual points. These are the medians for the bulges, the medians for the bulge, for the disk, sorry, and for the quiescent and the star forming at different redshift. So you immediately see that, which is nice, that the black median over here lies in between both. Okay, so you have that for the star forming population, the bulges tend to be on average redder in UV and also redder in VG, which indicates that they are less star formation, but also indicates, if you believe this trend, more dusty eventually. And the blue and the disks are more in the star forming region. Now, if you go to the quiescent population, both components are in the quiescent region now. You have scatter over here, but the disks, the bulges have moved a little, not much, but the disk has moved towards the quiescent population. So this is telling you basically that the bulge, already when you are here, the bulge is already built. It has the same structural properties than a normal bulge in a quiescent population, and it's already started to quench. Now, you can average all these trends, and this is how disks and bulges relate for star-forming galaxies. So you see that at different redshifts. So each point here, the stars are the bulges, the circles are the disks, and this is how they connect at different redshifts. So you see this trend, which kind of goes parallel to the dust trend, but it still has some redder component. While this is the trend for the quiescent population. So the disk is already up, as you would expect. Now you can kind of so this conclusion, the conclusion from this is that bulges in the main sequence are close to quiescent. Disks still form stars, and when they are quenched, both disk and bulges are quiescent, which, as you would expect. Now you can go a step further in the speculation and try to convert the position of galaxies in the UVJ plane to specific star formation rates by just looking at galaxies which are close. And this is the UVJ UV plane color-coded by specific star formation rate. This is the global specific star formation rate computed in candles, and you see that there's a well correlation here. So galaxies, as you expect here, are low specific star formation rate. So now you can go for the bulges and the disks individually and see where they lie in this plane and compute according to the average specific star formation rate of neighbors, estimate a kind of UVGA-based specific star formation rate. And this is some histograms, very preliminary what you get. So this is the histogram of specific star formation rate for bulges, and this is for disks, so both living in the same galaxies. And you see this kind of trend. The dashed lines here that you don't see are the medians. So you see that they are kind of separated, but there's a lot of overlap, which is the noise I'm trying to figure out. Okay, I'm almost done. Next, also, you can, since we have the model for the bulge and the disk together, what you can also do is, instead of having integrated star formation, specific star formation rates, you can do radial trends. Okay, so you can integrate the model in annually and compute the UVJ and convert the specific star formation rate in the same manner. And this is a preliminary plot of this. So here now I'm showing here radial trends normalized to the effective radii of the galaxy. So one is effective radii for 2 redshift beams, stellar masses between 10.5 and 11. These are quiescent galaxies, median BT 0.5, and these are star forming. So same morphology, but same mass, same redshift. And these are the bulge radial profiles, these are the disks, and these are the average. Okay, this is very preliminary, so please take it, but I'm happy to get inputs from you. But what I've plotted here is what you typically use to select the threshold you select in specific star formation rate for passive galaxies. So basically, what you see here is that in this start, and then sorry, it's inverted. Yeah, sorry, I just realized it's inverted. Sorry for that. Okay, so I start again. These are star forming. These are quiescent. So change your brain, please. and what you see here, so for the star forming, sorry for that, the bulge is below the quiescent threshold, while the disk is forming stars. This is another view of, and this happens at all radii. Now, I was a bit puzzled by that, because at some point the bulge should dominate, which I don't understand, but I plotted here the typical effective radius of the bulge. So basically, this is the effective radius of the galaxy, of the total galaxy. This is the effective radius of the bulge. So already here, the light of the bulge is half of its total light. So all the light of the bulge is in very central parts. So basically, you know, to embed, probably there's a resolution issue here. So probably in order to see that the bulge completely dominates the specific star formation rate, you need to go very in the inner centers. So again, this is for the quiescent population, and you see again the same trend. Everything goes down basically. Also the bulge, so it still goes down, but everything is below this threshold. So I'll stop here. These are my conclusions. So basically, the takeaway messages is that bulges start growing the main sequence. There are no passive pure disk galaxies, so the quenching channel without building a bulge is not common. Maybe during this growth of bulge, black hole grows at the same time, don't know. Bulge growth does not care much about the disk, so the mechanisms that build the bulge are kind of similar for all types of galaxies, and bulges in the main sequence tend to be already passive and with the structural properties in place. Thank you.
Thanks. Okay, do we have any questions for Marc? I think we have time for at least two. David?
I was going to say that the age is involved play a role.
Exactly.
So you could take out from epic to epic, you take away the moving component that you can see where the new balls
Right.
rise from.
Right. Yeah, exactly. So the point is constraining the ages with this broadband photometry is very tricky. Already I don't trust the SFRs, but we are trying to fit the SCDs now with, you know, SHARP survey, which have many narrow band filters. So maybe this could be a way.
You have an estimate how long it will last. You know how many there are. So you can take
Right.
the population, subtract it to the next
Right.
later time to see what the differential.
Right.
Do you have time for a quick question? Okay, Abhishek.
How do you reconcile your last conclusion with the existence of blue nuggets?
The last conclusion, so.
There is a really compact object like nuggets in the main.
Yeah, so what you see here, this is the sigma 1 plot, okay? And you see that the bulge is growing at the same time that sigma 1, so your blue nuggets are here, okay? And you have, so intermediate, so for, this means that for intermediate B over T's, what I'm trying to say here is that the bulge component, what I mean, sorry? So yeah, exactly, and that the bulge component, the mechanism that build the bulge doesn't, it's kind of the same independently of the morphology. Or this is what we see here. So I don't see any signature in the mass size relation. Yeah, we can talk about that.
Okay.
Okay. Any examples of galaxies, or is there room in the analysis for systems where this is destroyed to create bulk, but the disk is subsequently regrown? It's always quite hard to estimate the underlying.
This you need the ages, I think. I don't have the ages of the disks. But yeah, this is something, but there's definitely room for destroy. I mean, the disk needs to be destroyed first because you have an excess of large V over T's that you don't see in the sequence. So these galaxies need to undergo merger or something, and then for some reaction.
Okay, let's move on to the next, and we can talk about these things during coffee. Okay. Okay, so now next up we have Michael Kretschmer.